Hydrogenation to treat with hydrogen is a chemical reaction between molecular hydrogen and another compound or element, usually in the presence of a catalyst such as nickel, palladium or platinum. The process is commonly employed to reduce or saturate organic compounds. Hydrogenation typically constitutes the addition of pairs of hydrogen atoms to a molecule, generally an alkene. Catalysts are required for the reaction to be usable. Non-catalytic hydrogenation takes place only at very high temperatures. Hydrogenation reduces double and triple bonds in hydrocarbons. Because of the importance of hydrogen, many related reactions have been developed for its use. Most hydrogenations use gaseous hydrogen, but some involve the alternative sources of hydrogen, not H2. These processes are called transfer hydrogenations. The reverse reaction, removal of hydrogen from a molecule, is called dehydrogenation. A reaction where bonds are broken while hydrogen is added is called hydrogenolysis, a reaction that may occur to carbon-carbon and carbon-heteroatom bonds. Hydrogenation differs from protonation or hydride addition. In hydrogenation, the products have the same charge as the reactants. Hydrogenation of unsaturated fats produces saturated fats. In the case of partial hydrogenation, trans fats may be generated as well. Process: hydrogenation has three components: the unsaturated substrate, the hydrogen and, invariably, a catalyst. The reduction reaction is carried out at different temperatures and pressures depending upon the substrate and the activity of the catalyst. Substrate: the addition of H2 to an alkene affords an alkane in the prototypical reaction, RCH equals CH2 plus H2 RCH2CH3. Hydrogenation is sensitive to steric hindrance, explaining the selectivity for reaction with the exocyclic double bond but not the internal double bond. An illustrative example of a hydrogenation reaction is the addition of hydrogen to maleic acid to form succinic acid. Numerous important applications of this petrochemical are found in pharmaceutical and food industries. An important characteristic of alkene and alkene hydrogenations, both the homogeneously and heterogeneously catalyzed versions, is that hydrogen addition occurs with syn addition, with hydrogen entering from the least hindered side. Typical substrates are listed in the table. Catalysts, with rare exceptions, no reaction below 480 AA degrees Celsius occurs between H2 and organic compounds in the absence of metal catalysts. The unsaturated substrate is chemisorbed onto the catalyst, with most sites covered by the substrate. In heterogeneous catalysts, hydrogen forms surface hydrides from which hydrogens can be transferred to the chemisorbed substrate. Platinum, palladium, rhodium, and ruthenium form highly active catalysts, which operate at lower temperatures and lower pressures of H2. Non-precious metal catalysts, especially those based on nickel, have also been developed as economical alternatives, but they are often slower or require higher temperatures. The trade-off is activity versus cost of the catalyst and cost of the apparatus required for use of high pressures. Notice that the rainy nickel catalyzed hydrogenations require high pressures. Two broad families of catalysts are known: homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts dissolve in the solvent that contains the unsaturated substrate. Heterogeneous catalysts are solids that are suspended in the same solvent with the substrate or are treated with gaseous substrate. Homogeneous catalysts. Illustrative homogeneous catalysts include the rhodium-based compound known as Wilkinson's catalyst and the iridium-based Crabtree's catalyst. An example is the hydrogenation of carbon. Hydrogenation is sensitive to steric hindrance, explaining the selectivity for reaction with the exocyclic double bond but not the internal double bond. The activity and selectivity of homogeneous catalysts is adjusted by changing the ligands. For prochiral substrates, the selectivity of the catalyst can be adjusted such that one enantiomeric product is favored. Asymmetric hydrogenation is also possible via heterogeneous catalysis on a metal that is modified by a chiral ligand. Heterogeneous catalysts. Heterogeneous catalysts for hydrogenation are more common industrially. As in homogeneous catalysts, the activity is adjusted through changes in the environment around the metal, that is the coordination sphere. Different phases of a crystalline heterogeneous catalyst display distinct activities, for example. Similarly, heterogeneous catalysts are affected by their supports, that is the material upon which the heterogeneous catalyst is bound. In many cases, highly empirical modifications involve selective poisons. Thus, a carefully chosen catalyst can be used to hydrogenate some functional groups without affecting others, such as the hydrogenation of alkanes without touching aromatic rings, or the selective hydrogenation of alkanes to alkanes using Lindlar's catalyst. For example, when the catalyst palladium is placed on barium sulfate and then treated with quinolin, the resulting catalyst reduces alkanes only as far as alkanes. The Lindlar catalyst has been applied to the conversion of phenylacetylene to styrene. Asymmetric hydrogenation is also possible via heterogeneous catalysis on a metal that is modified by a chiral ligand. Hydrogen sources. For hydrogenation, the obvious source of hydrogen is H2 gas itself, which is typically available commercially within the storage medium of a pressurized cylinder. The hydrogenation process often uses greater than 1 atmosphere of H2, usually conveyed from the cylinders and sometimes augmented by booster pumps. Gaseous hydrogen is produced industrially from hydrocarbons by the process known as steam reforming. Transfer hydrogenation. Hydrogen also can be extracted from hydrogen donors in place of H2 gas. Hydrogen donors, which often serve as solvents, include hydrazine, dihydronaphthalein, dihydroanthracene, isopropanol, and formic acid. In organic synthesis, transfer hydrogenation is useful for the asymmetric reduction of polar unsaturated substrates, such as ketones, aldehydes, and imines. Electrolytic hydrogenation. Polar substrates such as nitriles can be hydrogenated electrochemically, using protic solvents and reducing equivalent as the source of hydrogen. Thermodynamics and Mechanism. Hydrogenation is a strongly exothermic reaction. In the hydrogenation of vegetable oils and fatty acids, for example, the heat released is about 25 kilocalories per mole, sufficient to raise the temperature of the oil by 1.6 a euro 1.7 a degrees Celsius per iodine number drop. The mechanism of metal catalyzed hydrogenation of alkanes and alkanes has been extensively studied. First of all, isotope labeling using deuterium confirms the regiochemistry of the addition, RCH equals CH2 plus D2 RCH DCH2D, heterogeneous catalysis. On solids, the accepted mechanism is the Hauruti-Polymer mechanism, binding of the unsaturated bond, and hydrogen dissociation into atomic hydrogen onto the catalyst, addition of one atom of hydrogen. This step is reversible, addition of the second atom. Effectively irreversible under hydrogenating conditions. In the second step, the metal intermediate formed is a saturated compound that can rotate and then break down, again detaching the alkane from the catalyst. Consequently, contact with the hydrogenation catalyst necessarily causes Si-trans isomerization, because the isomerization is thermodynamically favorable. This is a problem in partial hydrogenation, while in complete hydrogenation the produced transalkane is eventually hydrogenated. For aromatic substrates, the first bond is hardest to hydrogenate because of the free energy penalty for breaking the aromatic system. The product of this is a cyclohexadiene, which is extremely active and cannot be isolated. In conditions reducing enough to break the aromatization, it is immediately reduced to a cyclohexane. The cyclohexane is ordinarily reduced immediately to a fully saturated cyclohexane, but special modifications to the catalysts can preserve some of the cyclohexane, if that is a desired product. Homogeneous catalysis. In many homogeneous hydrogenation processes, the metal binds to both components to give an intermediate alkane metal, H2 complex. The general sequence of reactions is assumed to be as follows or a related sequence of steps: binding of the hydrogen to give a dihydride complex, LNM plus H2 LNMH2, binding of alkane, LNM, I2 hours 2, plus CH2 equals CHR LN1MH2, CH2 equals CHR, plus L, transfer of one hydrogen atom from the metal to carbon, LN1MH2, CH2 equals CHR, and LN1M, H, CH2CH2R, transfer of the second hydrogen atom from the metal to the alkyl group with simultaneous dissociation of the alkane, Ln1M, H, CH2CH2R, and Ln1M plus CH3CH2R, preceding the oxidative addition of H2 is the formation of a dihydrogen complex. In organic substrates, the hydrogenation of nitrogen to give ammonia is conducted on a vast scale by the Haber-Bosch process, consuming an estimated 1% of the world's energy supply. Oxygen can be partially hydrogenated to give hydrogen peroxide, although this process has not been commercialized. Industrial applications. Catalytic hydrogenation has diverse industrial uses. Most frequently, industrial hydrogenation relies on heterogeneous catalysts. In petrochemical processes, hydrogenation is used to convert alkenes and aromatics into saturated alkanes and cycloalkanes, which are less toxic and less reactive. For example, mineral turpentine is usually hydrogenated. Hydrocracking of heavy residues into diesel is another application. In isomerization and catalytic reforming processes, some hydrogen pressure is maintained to hydrogenolyze coke formed on the catalyst and prevent its accumulation. Hydrogenation is a useful reaction for converting more oxidized oxygen and nitrogen compounds such as aldehydes, imines and nitriles into the corresponding saturated compounds, that is alcohols and amines. Primary alcohols can be synthesized from aldehydes by hydrogenation. Thus, alkylaldehydes, which can be synthesized with the oxo process from carbon monoxide and an alkene, can be converted to alcohols. For example, 1-propanol is produced from propionaldehyde, produced from ethane and carbon monoxide. Xylitol, a polyol, is produced by hydrogenation of the sugar xylose, an aldehyde. Primary amines can be synthesized by hydrogenation of nitriles, while nitriles are readily synthesized from cyanide and a suitable electrophile. For example, isophorone-diamine, a precursor to the polyurethane monomer isophorone disocyanate, is produced from isophorone nitrile by a tandem nitrile hydrogenation reductive amination by ammonia, wherein hydrogenation converts both the nitrile into an amine and the amine formed from the aldehyde and ammonia into another amine. In the food industry, the largest scale application of hydrogenation is for the processing of vegetable oils. Typical vegetable oils are derived from polyunsaturated fatty acids. Their partial hydrogenation reduces most but not all of these carbon-carbon double bonds. The degree of hydrogenation is controlled by restricting the amount of hydrogen, reaction temperature and time, and the catalyst. Hydrogenation converts liquid vegetable oils into solid or semi-solid fats, such as those present in margarine. Changing the degree of saturation of the fat changes some important physical properties such as the melting range, which is why liquid oils become semi-solid. Solid or semi-solid fats are preferred for baking because the way the fat mixes with flour produces a more desirable texture in the baked product. Because partially hydrogenated vegetable oils are cheaper than animal source fats, are available in a wide range of consistencies, and have other desirable characteristics, they are the predominant fats used as shortening in most commercial baked goods. Health implications. A side effect of incomplete hydrogenation having implications for human health is the isomerization of some of the remaining unsaturated carbon bonds. The psi configuration of these double bonds predominates in the unprocessed fats in most edible fat sources, but incomplete hydrogenation partially converts these molecules to trans isomers, which have been implicated in circulatory diseases including heart disease. The conversion from psi to trans bonds is favored because the trans configuration has lower energy than the natural psi1. At equilibrium, the trans-psi isomer ratio is about 2:1. Food legislation in the US and codes of practice in EU have long required labels declaring the fat content of foods in retail trade and, more recently, have also required declaration of the trans fat content. The use of trans fats in human food products has been effectively banned in Denmark and Switzerland. In the US, local legislation banned trans fats from restaurants and public kitchens in New York City and California. other countries and regions have introduced mandatory labeling of trans fats on food products and appealed to the industry for voluntary reductions. Hydrogenation of coal. History: Heterogeneous catalytic hydrogenation. The earliest hydrogenation is that of platinum-catalyzed addition of hydrogen to oxygen in the Dar paragraph Berryner's lamp, a device commercialized as early as 1823. The French chemist Paul Sabatier is considered the father of the hydrogenation process. In 1897, building on the earlier work of James Boyce, an American chemist working in the manufacture of soap products, he discovered that the introduction of a trace of nickel as a catalyst facilitated the addition of hydrogen to molecules of gaseous hydrocarbons in what is now known as the Sabatier process. For this work Sabatier shared the 1912 Nobel Prize in Chemistry. Wilhelm Naumann was awarded a patent in Germany in 1902 and in Britain in 1903 for the hydrogenation of liquid oils, which was the beginning of what is now a worldwide industry. The commercially important Haber-Bosch process, first described in 1905, involves hydrogenation of nitrogen. In the Fisker-Trop process, reported in 1922, carbon monoxide, which is easily derived from coal, is hydrogenated to liquid fuels. Also in 1922, Voorhees and Adams described an apparatus for performing hydrogenation under pressures above 1 atmosphere. The Parr shaker, the first product to allow hydrogenation using elevated pressures and temperatures, was commercialized in 1926 based on Voorhees and Adams' unregistered trademark research and remains in widespread use. In 1924 Murray Rainey developed a nickel fine powder catalyst named after him which is still widely used in hydrogenation reactions such as conversion of nitriles to amines or the production of margarine. Homogeneous catalytic hydrogenation. The history of homogeneous hydrogenation has been assigned to the development the Murray Pondor for early reduction of ketones using aluminium oxides. In the 1930s, Calvin discovered that copper, 2, complexes oxidized H2. The 1960s witnessed the development of well-defined homogeneous catalysts using transition metal complexes, for example, Wilkinson's Catalyst 3. Soon thereafter Schrock and Opsorns discovered that cationic RH-ing to catalyze the hydrogenation of alkanes and carbonyls. In the 1970s, asymmetric hydrogenation was demonstrated in the synthesis of LDOPA. In the 1990s saw the invention of Neue asymmetric hydrogenation. The development of homogeneous hydrogenation was influenced by work started in the 1930s and 1940s on the OXO process and Ziegler-Uranatter polymerization. More recently, homogeneous hydrogenation has been used to promote reductive C-C bond formation. Metal-free hydrogenation. For all practical purposes, hydrogenation requires a metal catalyst. Hydrogenation can, however, proceed from some hydrogen donors without catalysts, illustrative hydrogen donors being diamide and aluminium isopropoxide. Some metal-free catalytic systems have been investigated in academic research. One such system for reduction of ketones consists of tert-butanol and potassium tert-butoxide in very high temperatures. The reaction depicted below describes the hydrogenation of benzophenone. A chemical kinetics study found this reaction is first order in all three reactants, suggesting a cyclic 6-membered transition state. Another system for metal-free hydrogenation is based on the phosphine-boron, compound 1, which has been called a frustrated Lewis pair. It reversibly accepts dihydrogen at relatively low temperatures to form the phosphonium borate 2, which can reduce simple hindidimines. The reduction of nitrobenzene to aniline has been reported to be catalyzed by fullerene, its monoanion, atmospheric hydrogen and UV light. Equipment used for hydrogenation. Today's bench chemist has three main choices of hydrogenation equipment: batch hydrogenation under atmospheric conditions, batch hydrogenation at elevated temperature and/or pressure, flow hydrogenation, batch hydrogenation under atmospheric conditions. The original and still a commonly practiced form of hydrogenation in teaching laboratories. This process is usually effected by adding solid catalyst to a round bottom flask of dissolved reactant which has been evacuated using nitrogen or argon gas and sealing the mixture with a penetrable rubber seal. Hydrogen gas is then supplied from a H2-filled balloon. The resulting three-phase mixture is agitated to promote mixing. Hydrogen uptake can be monitored, which can be useful for monitoring progress of a hydrogenation. This is achieved by either using a graduated tube containing a colored liquid, usually aqueous copper sulfate, or with gauges for each reaction vessel. Batch hydrogenation at elevated temperature and/or pressure, since many hydrogenation reactions such as hydrogenolysis of protecting groups and the reduction of aromatic systems proceed extremely sluggishly at atmospheric temperature and pressure, pressurized systems are popular. In these cases, catalyst is added to a solution of reactant under an inert atmosphere in a pressure vessel. Hydrogen is added directly from a cylinder or built-in laboratory hydrogen source, and the pressurized slurry is mechanically rocked to provide agitation, or a spinning basket is used. Heat may also be used, as the pressure compensates for the associated reduction in gas solubility. Flow hydrogenation. Flow hydrogenation has become a popular technique at the bench and increasingly the process scale. This technique involves continuously flowing a dilute stream of dissolved reactant over a fixed bed catalyst in the presence of hydrogen. Using established HPLC technology, this technique allows the application of pressures from atmospheric to 1450 SI. Elevated temperatures may also be used. At the bench scale, systems use a range of pre-packed catalysts which eliminates the need for weighing and filtering pyrophoric catalysts. Industrial reactors, catalytic hydrogenation is done in a tubular plug flow reactor packed with a supported catalyst. The pressures and temperatures are typically high, although this depends on the catalyst. Catalyst loading is typically much lower than in laboratory batch hydrogenation, and various promoters are added to the metal, or mixed metals are used, to improve activity, selectivity and catalyst stability. The use of nickel is common despite its low activity, due to its low cost compared to precious metals. Gas-liquid induction reactors are also used for carrying out catalytic hydrogenation. See also, carbon-neutral fuel, dehydrogenation, transfer hydrogenation, hydrogenolysis, hydrodesulfurization, hydrotreater and oil desulfurization, timeline of hydrogen technologies, Josip Ligens, references. Further reading, Zhang S., Yung Mai, Mindy B. Hydrogenation for low trans and high conjugated fatty acids. Comprehensive Reviews in Food Science and Food Safety 1. Examples of hydrogenation from Organic Syntheses, Coal. Volume 7, pages 226. Organic Syntheses, Coal. Volume 8, pages 609. Organic Syntheses, Coal. Volume 5, pages 552. Organic Syntheses, Coal. Volume 3, pages 720. Organic Syntheses, Coal. Volume 6, pages 371. Early work on transfer hydrogenation, Davis, R.R. Hodgson, H.H.J. Chem. Soc 1943, 281. Leggetter, B.E. Brown, R.K. Can. J. Chem 1960, 38, 2363. Kuhn, L.P.J.M. Chem. Soc 1951, 73, 1510. Cumro, Fred August. Cumro, Gene M. Cholesterol won't kill you, but trans fat could. Trafford. ISBN A978-1-4251-3808-0. External links, The Magic of Hydropopular Mechanics, June 1931, pages 107 109 early article for the general public on hydrogenation of oil producers in the 1930s.